Okay, let's go ahead and get started. Today we're going to jump into a performance analysis. If you took Java with me, you've already done a little bit of this with Big O, but we're going to really go through it and make sure you understand it thoroughly what performance analysis is. And then we're going to talk about a couple of tools in order to help you do performance analysis, gprof, and which will actually do profiling. It'll tell you where your program is spending most of its time. And then there's GNU plot, which is just used to plot certain graphs, and I'll show you how inside your C code you can spit out timing results real fast, and then you can use GNU plot to give you a graph to show you what's going on. And then just some quick tips and gotchas to make things easier and hopefully avoid some issues that you may come up with. Okay. So we've gone into data structures. You've talked a little bit about algorithms. A dilemma you may come up with, hopefully at some point in your career, is that you have two or more methods to solve a problem. How do you choose which one is best? How do y'all choose which one's best?
Whichever one works.
Whichever one works. What if they both work?
And the simpler one is better.
The simpler one, okay. The simpler one that
Performs better.
The teacher knows.
Less resources.
the teacher knows. Okay. So yes, those are definitely the first things to jump to. Simpler and it works, especially if it fulfills your requirements. But in data structures or in algorithms, we do analysis based on performance. So if we're trying to figure out the performance of two algorithms, they both work, and we don't really care about their simplicity at this moment, just the fact that we can use them. How would you test that?
Oh, test to see if it was simpler?
Test to see which one's better or faster.
Whichever one requires less resources.
Requires less resources. Ooh. Well, some programs, some algorithms actually require more memory but run a lot faster.
Whatever their O is.
Whatever their O is, their big O is, right. What is that all about?
That's like how many steps it takes to go through it. Or how many
So you do some analytical analysis of the
Counting.
yeah. That sounded great, didn't it?
Yeah.
Of the actual algorithm and try and figure out which one's better. Okay. So one approach I was trying to get to is you can implement each algorithm in C or whatever language you want and test how long it takes each one to run. And this can work, but you may have different implementations, which would cause the algorithm to run faster or slower. Some algorithms run faster on some computers and slower on other computers. And they may also perform differently on data. So the problem here is there's a lot of actual variance when you use with your computers that can cause your algorithm to perform either faster or slower. So you need to really determine which one's best. So the way we do this is we usually categorize by key operations. For example, if we go into sorting, you count the number of times two values are compared or the times two values are swapped. You'll assume, of course, that those are the expensive operations. Searching, number of times value being searched for compared to values in an array. So how many times do you actually have to do a compare? And then if you're doing recursion, you probably count the number of recursive calls, assuming your recursive function is very simple, of course. So we want to come up with a general performance, measure several examples. What does this tell us in general? Yeah, so empirical would be run through a bunch of examples. But what does this tell us in general? It may not give us a clear view because your data set may not be wide enough to capture everything. Good morning.
Good morning. You have a story? Yeah.
Punishment for coming in late.
Permission to speak freely, sir.
I am recording, but yes.
I forgot to go to a morning announcement, sir.
What announcement was this?
That data structures sucks.
Wow, that was brutal. Whew. You didn't get your labs done? Is that what you're trying to tell me?
What?
You didn't get your labs done? Is that what you're trying to tell me?
No, I'm not labs done. I just
Oh.
have trouble submitting one a little bit.
So the empirical way is run a bunch of times, figure out, maybe you can get an idea of which one's faster, although as I'll show you in a bit, that may not be the case because you may not be able to search wide enough, especially if you're trying to figure out which algorithm is going to be faster over the course of weeks. So analytical is instead we add, well, basically, we look at the problem and try and analyze how often searching and comparing are going to be performed. It may be difficult to discover a reasonable formula, but as you'll see, there's a lot of assumptions we can make to simplify the whole process. Okay, for sorting, a sorting routine may require as few as n minus 1 comparisons and as many as n squared over 2. And when we talk about analysis, we're usually looking at best case, average, and worst, or worst case. Worst case. Worst.
Hey, at least it's spelled right.
Hey, it is spelled right. Yes.
Wait, you actually got something right for once?
Yeah, I didn't put an E
No,
there.
the problem is when you copy from under one slide.
And then it becomes Warset.
No, because he does have his moments.
Anyways, we do best
I
case.
bet he is Hayes. Oh my gosh. Spelling errors.
We forget to run spell checkers. I'm sorry. We get excited about this step, all right? Best case, if the algorithm is able to solve it really fast. Average case, in general, 80 to 90% of the time, what you expect it to do. And then worst case, if you give it something really terrible, will the algorithm really slow down? In general, we usually think of worst case because a lot of times our programs are
Run in worst case.
well, it's like if it's a piece of health equipment, you want to know what the worst case is for when, in case
For
something
when
really,
the worst case happens.
for when the worst case happens, because that's why you're using it to begin with. All right. I want to make sure it's clear. We are actually doing an estimation when we do Big O or analytical analysis. We're not going to be exact. I'll try and be very exact at first and then show you why that is actually really annoying and complicated and hard to do. And therefore we don't.
Complicated.
Huh?
Because things get complicated.
Things are complicated.
It's the way of life.
And so estimation is an important skill. A good example here is how many hot dogs tall is the Empire State Building?
What?
A lot.
Yeah. How tall is it? Yes.
Depends on the type of
Make
hot
an
dog.
algorithm for it.
Make it. Make it.
Are we talking like foot-long hot dogs, or are we talking about like the regular size ones?
Well.
Because there's like bun length hot dogs, there's like regular hot dogs, there's like foot-long hot dogs.
Right.
Like,
Right. Well, I didn't ask that, right? I just,
Exactly.
huh?
How are they being stacked?
are they like this? Are they like this? How is it balancing?
Dr. West, well, first we need to find out how tall the Empire State Building is, how
Imagine
tall
you stack hot dogs.
an average hot dog
It's
is,
rounded, it's
whether or not
rounded.
you're using a linked list, a stack, a queue.
I'm glad y'all. I'm glad I chose this example. This was great. Because exactly, it's like y'all read the next slide. So a simpler question is, how tall is the Empire State Building? I think, 1,250 feet tall.
So
roughly.
if you have foot-long hot dogs, it's about.
Well, we're saying if you
1,250
assume a hot dog
if you
6
stack it like
inches
this.
and you stack it from end to end, so it's 2 times. that.
And if it balances, you gotta take
just
the
assume
wind
that
and
they're
everything.
tied together or something.
Oh, okay.
Okay.
They're tied around a pole.
They're tied around a
A very,
pole.
very tall pole.
Pole that's very strong. That can take the weight of 2,500
I just
hot
imagine
dogs.
the pole with hot dogs just swinging back.
It's like this the whole way. So that's a good way to estimate.
Just imagine how nice students.
All right, so is it actually 2,500 hot dogs tall?
No.
Probably not. Maybe. Probably
Well, if
not.
you have foot-long hot dogs, it's not, because it means
Sure.
150.
But it's a good estimation, right? And that's what we're trying to point out when we do performance analysis, and analytically at least. We're just estimating here.
No, I feel like it should be a lot more.
2,500 is a small number.
I mean,
That's
yeah.
good. That's a sign of a good computer science.
I just
You know,
imagine
2,500
someone
is now
reaching out a
small.
window.
My son's like, 100 is huge. Okay.
Just wait, it goes up to 200.
Hold on. Morning.
Morning.
Story.
Sorry.
See, what happened was when I left my dorm this morning, it was like a wild Snorlax in front of my door.
Snorlax?
Yeah. So I had to like fire my pookie fluid to wake it up.
Okay.
And after I woke it up, it was kind of bad, so I had to like paint it. And
Did you capture it?
no.
No.
I thought it was better if I just fainted. It won't come back.
Still
No,
my
that's
favorite
dead.
figure for you.
No,
No,
that's dead. There's a
That's
difference.
faint. Faint is different.
If
is
it doesn't
fainted.
come back, it's dead.
That's not a fake. That's just.
Straight up dead.
Wow.
We talked about this last semester.
Yes, apparently it was a big deal. All right, complexity analysis. Basically, complexity analysis, we're doing two types. Algorithm, which is the, think of it of how many mathematical computations your program has to do, how many times it has to compare, equal, add, subtract, et cetera, et cetera. Wait, that's complexity.
Okay. Next.
But really, that's what I'm talking about when we do a complexity analysis. Space analysis is how much memory it takes up. Some algorithms only take up a single array. Sometimes you're going to have a very complex data structure which will consume a lot of memory.
And then your computer is bad.
And then your computer may slow down.
That's not what I said.
All right, when we do this algorithm analysis, please understand that there is no set of rules. There's no generally accepted rules to do this analysis, unfortunately. So we're just going to approximate. I'm going to give you a set of general rules that work. So please, for this class, just stick with those. I'm not going to ask you to come up with something crazy. And we'll just go through those. So the rules. First off, we assume an arbitrary time unit. AKA, we're assuming that addition, subtraction, multiplication, division, equality all consume the same amount of time in order to execute. Do you think that's correct?
Probably not.
When you take computer architecture, you'll find out that is absolutely not correct whatsoever. But for our analysis, at least in this class, it's actually just fine to assume they all take 1 unit of time.
Sure. Whatever you say.
Whatever. And that's probably the biggest assumption we make that actually makes the rest of our lives a lot easier while doing this. Way.
Just ignore the tree.
Well, they all take, well, no, they don't all take constant time either. But that's okay.
That's a different thing.
I was going to say, in general, I was going to say addition takes, well, I should say multiplication in general takes 20 to 50 times longer than addition, but that's not always the case either. Function return.
It depends.
It depends. But, it's okay for this class to just assume they all take the same amount of time. Okay. We assume running time of selection statement, if and switch, is the time for the condition plus the maximum running time of the individual clauses in the section. So if you're trying to figure out how long an if statement takes to execute, you say how long does it take to evaluate the expression in it, and then how long does it take to execute the code inside of it, and you add that up.
Magic.
It's magic.
Oh, that's me.
Loop execution. Wait, actually, any questions about if? Hopefully that's strict. We'll go through some examples soon. Loop execution, the sum over a number of times of the body plus the time to do the check. So in other words, you're going to have your check, and your check is going to be done a certain number of times, and then your body will be run a certain number of times as well, so you got to add all that up. Always assume the loop executes a maximum number of iterations possible, so you're going to have to find an upper bound when you're thinking about your loop. Most of the time, at least in this class, that's going to be pretty obvious.
Where are these PowerPoints?
They are up on GitHub. If you do a pull from upstream, you should get it. It's called 05, I think, performance analysis. It's under, okay, you know what, let's go on GitHub. GitHub.
Your folder with PowerPoints is not these.
Let's go, let's see. Lectures, PDF. Oh, it's a PDF. 05 performance analysis.
Okay.
Shut it down.
Okay, so quick calculation here. Count equals count plus 1, and then sum equals sum plus count. We're saying that the first line has a cost of C1, and the second line has a cost of C2. So the total cost would be C1 plus C2.
Whoa.
We assume addition has a cost of 1, assignment has a cost of 1, the total cost is therefore 4. What are the 4 things?
Why is it C? Why
First.
did you put O?
What?
What?
Why are we doing C's?
What do you mean?
For costs? prefer?
I'm thinking of the,
All right, why is the cost 4?
Yeah, we're not doing
Three or four things happening.
4 things are happening. What are the 4 things?
We have the count.
setting equal.
You're setting the variables and you're adding count with count plus 1. So it should be a cost of 2 per line.
Right, so there's a plus here, that's 1. There's an assignment here, that's 2. There's another addition here, that's 3. And then there's another assignment here, that's 4. So the cost here is 4. Everyone good?
Yeah.
All right. How about this?
Oh. Never mind. Let's go back to the
One,
It just has a lot of notes in order to...
three. I only see 3.
So
Comparison and 2 assignments.
So it's an if statement. The total cost is the cost of C1, aka doing the evaluation, plus the max of either C2 or C3. So we have to figure out which one, 2 or 3 is the max. Well, C1 is just the cost of the Boolean evaluation, but there's only one evaluation less than it, so the cost of C1 is 1. All right? Awesome.
The worst case is 3.
Right. C2, the cost of negating a number is 1. Oh, let me do this with my mouse pointer so people see it. The cost of negation is 1, and then you have assignment, which is 2. So the cost of C2 is 2. The cost of C3, we're just doing assignment, therefore the cost is 1. Therefore, the max of 1 and 2, aka C2 costs the most 2. It would be 1 plus 2, and therefore worst case is 3. Best case is 2 if it jumped down to C3 instead. And then you could say the average cost is 2.5.
You should get like a laser pointer. Point the
Yeah, but the people online won't be able to see the laser pointer.
They should come
Get a
with
big
us.
stick.
The big stick. Put it in, stab my machine. Any questions on this one?
Say that.
Actually, what is it? It's,
That's a-
I can't remember if it was PowerPoint or if it was like Keynotes or
No.
just the Mac one where you actually can turn your pointer into a laser pointer.
Well, that's the music.
It's awesome.
Any questions on this one?
Have too much fun.
Good so far?
I'm pretty sure it's Keynote.
All right, how about this one? What's the cost of C1?
1.
And
I should have also asked, how about C2? Okay, I put it up on the board.
Oh, yeah. Everything is 1.
Well, C1, C2, and C3 are all
3
1.
is 2.
4 is 2.
4 is 2, 5 is...
2.
All right, let's see if I give you too many...
4, 6, 8.
Yeah, so cost is 2. C4 is 2, sorry. C5 is 2. All right, well, what's the actual total cost?
C3 is.
It's 7.
It depends.
Well, yeah. Worst
depends.
case
Wait,
is 7.
Always take the worst case.
Is C3 only 1 even though it's.
Yeah, we're only evaluating the Boolean expression, but we're trying to figure out the cost of... How did I... See, how many times does a loop execute?
Oh. Good question.
10 times. So the total cost is... Ooh, who can get this formula?
7N.
7n.
7 plus. No,
Wait.
Wait.
Just 7.
Hold on, has n... Do you know what n is?
Yeah.
No.
No. So you must come up with a formula that involves n.
3 plus 4.
3 plus... Wait, what? No, 3 plus...
4N.
3
No,
plus
3
4.
plus 4.
Okay, 4n. Oh, where'd you get the 4? That was a good...
That was from the cost of C4 and C5.
Okay.
What about C3?
Sorry,
2 plus 5 then.
C3.
Yeah, 5n, because you got to get the cost of... All right, so you have... What do we say? 3 plus...
2 plus 5N.
So you have 2 plus 5n.
Yes.
would it be 4n plus 2?
4n plus 2. Man, we're taking a lot of guesses here. Okay. Let's start back. All right, I think we all got that C1, C2 cost 2. So there's that plus 2 right there. Good. For each iteration of this loop, what's the cost?
5.
5, because you got to execute C3, which is 1. C4 is 2. C5 is another 2 for a total of 5. So each iteration of this loop costs 5. Now, so 5n. So right now we have 2 plus 5n. Are we missing anything? We're missing one last thing.
Plus 1.
Plus 1. Why are we adding 1?
It's the last time when it actually doesn't fulfill the
While.
while, it will still check that.
Everyone see that? There's that one extra check at the end. That happens. So it's 2 plus 5n plus 1, and I think I wrote it differently. Another way to think of that, C1 plus C2 plus 2 plus 1, n plus 1, C3, because that's how many times C3 is actually being evaluated, n plus 1 times. Then it's n times C4 plus n times C5. So you can pull it out to this formula, or, well, I didn't actually write the last one, but then, yeah, it would be, what was it, 3 plus 5n? Okay. Any questions on that?
With the Boolean check.
What?
No, with the Boolean check, that's why it's a plus 1. Or that's why
Yeah.
it's 5n plus 3.
Yeah,
5n
because
plus 2. Okay.
yeah, because C3 has to be checked that one last time.
Yep.
All right. Okay, here we go again. What's C1?
Squared.
I'm good you can just see it and do it, but let's actually do the full analysis here. Which, actually, this one's going to be real tricky. But we'll go through it. Yeah, this one's tricky. Now, it's to show you why we do a lot of generalization and estimation, because just assuming 1 is going to get really tricky all of a sudden here. All right, what's the cost of C1?
1.
Cost of C2?
2.
1.
How does that even together?
Cost of C3? Cost of C4?
1.
Cost of C5? Man, we're doing great. Cost of, what's C6?
2.
C7?
2.
And C8.
2.
All right, so I wrote all those out. Y'all are doing awesome.
Woo!
Woohoo!
Great.
That was the fun part.
All right, now we got that taken care of.
Now we actually have
First while loop execution is in. So what does that mean?
It runs n times.
Yes. And then C3 is going to be executed
N plus 1.
n plus 1 times, right. N plus 1 times. The inner loop execution is in, so that means C5 is going to be run how many times? All right, so not quite. Where things get very confusing. Notice that, oh no, J starts at 1. Never mind. You're right. This is the one where J starts at 1. That's good. Not the one where J gets updated.
Oh my god.
Again, this is why this could start getting confusing. I'll try and explain this formula once, and y'all will probably glaze over, and that's perfectly fine. So C1 plus C2, those get executed once. That's great. C3 gets executed n plus 1 times. Awesome. Plus, and then what we have here, n times C4, because that's how many times C4 gets executed. Awesome. C5 is going to be executed n times in the body times n plus 1, which is how often that's executed, times C5, plus n times n of C6, plus n times C7, plus n times C8. Remember, that's on the outside of the while loop, so it's just n times C8. So it's actually not that bad. But you have to go, if you pull it all out and simplify it, you get C1 plus C2 plus C3 plus n times, C1 for C3, C4, C5, C8, and then n times n for C5, C6, C7. All right. Very important to realize that n squared is the highest, largest, or the dominating term. We'll get more to that later, but that's why I'm simplifying it this way.
What if I nest 3 loops? What if we nested 3 loops?
Then what would you think it'd be?
N cubed?
N cubed, yeah. You'd come out with something with n cubed in it.
Honestly, I never played.
All right, any questions on this? Doing good so far? Tracking? All right. Okay, so big O. We just measure the algorithm's time as a function of the problem size. Basically, when it comes down to it, we just start ignoring the constants in front of the variables and just pick the highest constant and then say that's what it is. But officially, why are we doing that? Well, the problem size depends on the application, number of elements. We could say the problem size, let's see, A requires 5 times n squared, and B is 7 times n. An algorithm's proportional time requirement is known as the growth rate. So we have to decide or start looking at what the growth rate of a function is. Which one is going to grow faster? Algorithm A or algorithm B?
Algorithm A.
Why is algorithm A going to grow faster?
You take the n to the squared. and that's why. Because it's squared, it runs faster. If you were to graph both of them, the y would go faster.
Right, the y would go fast. It's not going to grow fast. It's not going to go faster, but yeah, the growth function will increase substantially. So here's another question: which one of these is better?
The first one,
Why?
n to the third.
What?
No, the
No,
second
it's-
one's better because it doesn't have
Right now, the first one is still.
Ooh, and do the third is a no.
To the end.
But
it's-
it's
okay.
three
Yeah.
dead. So
They're both no-nos.
They're
Both are
not necessarily-
bad.
Both are bad. Right now, it may appear that both are bad, but if you had really complex algorithms that were solving a huge problem, and these are the two algorithms you came up with, which one would you prefer? First one. All right, let's see why that's the case. Well, it depends on n. If you actually start running it out, with 1, it actually, if n is just 1, you're only computing one thing, probably not doing too much. 170 computations versus 37, so it looks like the first one's winning. But once you start going down, where's the break? Right around 8, 19,000 versus 26,000, and all of a sudden 36,000 at 10, and oh my goodness, 236,000. So it looks like for very small numbers, the second one's better, but then afterwards, the first one's a lot better. Real quick, just to make sure why this is the case. When it comes down to it, in general, one term is going to dominate the other terms. Wait, what's on the left is not. Oh, yeah. No, this makes sense. Notice on the second one, I'm only taking 4 times into the third. 3 to the end. I'm only using that term, and I'm completely cutting out the rest of this right here. So I'm going to compare that whole value versus just this term right here. And you look at it. I'm sorry. Ignore what I just said. That was incorrect. I'm going to compare the whole term of the second one versus just 4 times 3 to the end. That's what I meant to say. So I'm taking this whole formula right here, copying, pasting it to right here, and then I'm just going to compare it to the other term right here. I'm going to compare the two. So total 37, that one takes account 12. You keep going down, eventually you get 236,000, the other one's 236,000, and just a little less. Notice that that third term is just zeroing in closer and closer to 100% of the actual total of the formula. What this means is that one term is really dominating everything else. So if we're doing a performance analysis, do we need to evaluate all the other terms or just the dominating term? Yeah, so we really only care about the dominating or the highest term, because once n becomes significantly large, the rest of it is basically irrelevant. Let's see, as n grows, some terms dominate. So here we have some common growth functions that you will encounter. You'll probably see all these in class at some point with different values of n. Notice that, once n is 100,000, the difference between each one is pretty absurd.
So 1 to n is the best in terms of
Yeah, 2 to the n, that's just not happening.
10 to the
Right here.
30,103
Yeah,
third power.
Whatever.
Third power.
you got it.
Yeah.
Yeah, that's how many zeros there are.
That's a lot of zeros.
That's a lot of zeros. So quick ordering. Hopefully this makes sense. 1, we consider less than log of n, which is less than n, which is less than n times log of n, less than n squared, less than n cubed, less than 2 to the n, less than 3 to the n. And I didn't put a factorial, but factorial would be over here somewhere. I'd have to look up. I think it's actually all the way to the right as well. Any questions about this ordering? Good.
I have a question.
Yes. I have answers.
On the n equals 100 and times log 2 and how is it 664 if log 2 and is 6? And
So log 2 n of 6, that's rounded.
Oh, okay.
It's not perfect.
Can you round it down?
I'm so sorry.
I think if it's 0.5 or above, we're always rounding it.
It's going to be okay. All right. So I'm going to go through the official definition, and then y'all are going to ignore it and just do what's the easy way, which is perfectly fine.
Just gonna ignore it.
That's okay. We got to go through the official definition anyways. So big O, officially, if you take, this is why discrete mathematics is important, so this notation makes sense. What?
I'm in that right now.
Yeah. Well, now you're going to learn why it's important.
It's so good.
Yeah, I'm in that next semester.
It's so important.
Literally.
So you have algorithm A requires time proportional to f of n, some function of n. Algorithm A is said to be an order of f of n if it's dominated by O of f of n. So what's this O f of n thing? Well, first off, f of n is the growth rate, aka that function we talked about earlier. Since capital O is used in this notation, the notation is called big O. So algorithm A requires proportional to n squared is O of n squared, aka the growth rate of f of n matches n squared. This should be a square over there. Right over here, that should be squared, not 2. That'd be silly. If its time is proportional to n, it's O of n. So putting some numbers to it for an example. Algorithm requires, let's see, n squared minus 3n plus 10 seconds to solve. If constants k and n naught exist, such that k times n times that formula is greater than n that formula plus 10, then for all n and n naught, then the algorithm is said to be order n squared. Everyone got that? Basically, if at some point we're saying that the function n squared plus some constant is going to always be larger than the other function, then you're saying that that other algorithm's O of n squared. Ta-da! All right, this isn't actually that hard. This may sound difficult, but once you understand the notation, you realize all you're doing is playing the game of spot the highest term. That's all. That's all you're doing. So the first one is O of n cubed. Why?
Because it's the highest term.
And cube is the highest.
Which term is that?
Is that?
31 times n cubed. All right. How about the next one? Why is it O of 3 to the n?
Because 3 to the n is the highest term.
All right. Yeah. Because 3 n. This can get somewhat tricky. Why is the first line n cubed?
Because there's 3 n.
Because
Distribute.
Yeah, you got to distribute out n. All right. So yeah, look, we can get a little complicated here.
Whoa.
I do math.
Whoa! You gonna be okay, Shay? Are you gonna be okay?
No.
Do you need a hug?
No.
I just asked if you needed one. I'm not offering.
Oh, okay, never mind. We're going back.
All right. Why is the next one n times log n?
Distribution of the first.
Again, distribution. All right. So make sure you distribute it out to separate terms, and that'll make some sense. All right. All right, real quickly, back of your head so you understand
Whoa.
what these mean. Yeah, it's a wall of text. If your algorithm's O of 1, that means you're doing awesome because it happens in constant time. We're done. Log of n requirements logarithmic, increases slowly as the problem size increases. It actually increases really slowly, so log of n is actually still pretty good. But O of 1 is still better.
Of course.
N
Is
just
there anything better than O1?
No.
technically no, because everything has to take constant time.
But there is. Technically, no.
Not
Numbers,
technically.
yeah.
Oh, okay, so the thing about O1 is you can start to divide it up into different sections. We say O of 1. If it takes 1,000,000 time units, it's still O of 1. If it takes 2 time units, it's still O of 1. But obviously the 2 time units is better than the 1,000,000. But we don't care about that when we're doing our estimation.
Okay.
Well, here you go.
But it's not like you can have O of -1. You have the answer before you ask for it. That doesn't make any sense. That'd be cool though. If you figure that out, tell me. We'll go get some research done, write some papers. It'll be awesome.
Get some, recognition.
Yeah, recognition.
Press, brain press.
Oh, then basically linear. There's some very close correlation between problem size and execution time. N times log n. It's a little more rapid than linear, but actually not that much. But it is significantly slower than linear, but not as bad as n squared. N squared is quadratic, so it's going to increase rapidly. n cubed, it's even more rapid than n squared. But the thing about n cubed is we still say that the problem or your algorithm is doable. And it'll still complete. It may take a day, but it'll still complete.
Run a program that takes 24 hours.
Hey.
That'd be
Hey,
so
if-
bad.
Well, I mean, let's just pretend for sake of argument that you were on Google and you were doing city to city, and that was just an n squared algorithm, just for sake of argument. Well, you could spend the time, compute all the answers, and then just store it, right, afterwards, and then you're just retrieving the answer later on. So that's not that bad, right? That's manageable. You can do things with that algorithm still. To the end, it's game over. Because
You lose.
you lose. Unless n is less than 20, maybe 30, maybe. That'd be pushing it. It's just not going to happen in your lifetime.
But it will eventually happen.
It will eventually happen. Unless it happens before the second coming, of course, which may actually at that rate. Yeah. All right.
I don't know what happens if it like tries to run and it gets to a certain point and then it like stops because of an error. Like,
Then you cry.
and it's like you're like dead already, and then you're like, oh my god, it's almost complete, like down to the last second, and it's like error found, and you're like, no.
Cry. Sick fault.
Last second. Make it even worse if the syntax error.
What would
you
be pretty
forgot
bad?
the semicolon.
Well, that would be a compile error, though. But it was interpreted. Oh yeah, that'd be terrible. Oh, that'd be worse than if you got the whole thing done and then the printout was wrong. Oh man. All right, let's go and do some examples now.
Fun people.
Yeah, but we're gonna do it again. What's the big? But we didn't talk about what the big O is. What's the big O of this?
And
N. Why is it an N?
because it's the highest term.
It's right. If you remember, highest term was N. It's A times N plus B, so the growth rate function of this algorithm is O of N. All right. That's a perfect example, simple example of how we're simplifying this. Are there any questions about this example? Yes.
How do you simplify it? Easy.
Example 2. How about this one?
N squared.
N squared. Why do we say it's N squared?
Well, we have a nested while loop.
That are based off of
And
N.
Yeah.
That are executed N times, or some function of N. Or some, linear correlation to N. Again, you multiply it all out, and then it's like A times N plus B times N plus C, so we're saying it's O of N. Everyone good?
Yep.
All right, let's change it up a little. Oh, and that's not changing it up at all. N what?
N to the third.
N cubed. So, yeah, this one actually gets a little complicated. I started estimating because I got tired of writing it out. But basically, C of 4 has N cubed in front of it, therefore it's N to the third. Notice we didn't need to know the exact number of iterations to find big O. No, a lot of times you just estimate, you're fine.
Keep guessing.
Keep guessing. All right, unfortunately, recursion can be hard. And this is why discrete mathematics is important, because it'll tell you how to solve these recursive functions. So what does this look like? Well, that code is actually kind of just not tabbed out well. All right.
Good job.
Thanks. I have worked so hard. Thanks. That's discrete mathematics. All right.
discrete structures.
Yeah. When I took it, it was called discrete structures. Now it's called discrete math. It's okay.
Yeah.
My university called it something different. All right. So first off, you must understand that there's a cost to a function call, and we'll just say it's constant for the sake of argument. I know. All right. So how many times is the function called per function call? Worst case. Whenever you do a function call, how many times is the function call. Remember, it's recursive, so the function is calling itself. Per each function call, how many times can it do another function call? Worst case.
Infinite times.
And
Okay, infinite times, but
2 per call?
hold on. Huh?
2 per call?
There's 2 function calls per a function call.
Oh, yeah.
See, you have, get the mouse
what's that
pointer.
function called?
So you call Hanoi,
Hanoi.
and there's one Hanoi here and another Hanoi there. So each time you call the function, it may be called twice. But how is n decreased? By 1. All right. So the relation is essentially 2 times t of n minus 1 plus some constant value. So it's 2 times n minus 1 plus c. I can show you how you solve this and prove that this turns out to be 2 to the n. But I'll let you do that when you take discrete math. Just know that if you have a function and it calls itself twice, inside of it, it's 2 to the n. If it called itself, well, not necessarily, but in this case, it is, because it's only decreasing n by 1 per every function call. If it was calling itself 3 times, what would it be? 3 to the n in this situation. But you're going to have to actually sit down and think about how it's moving down. And this will we'll go more into this when we jump into binary trees, because you'll be using recursive functions there. Okay. Any questions about Big O overall before I jump into gprof? No? All right. So let me go and